We're going to talk about a new class of reactions today. We're going to try to figure out how we can perform substitution reactions of alcohols. All right, so we want to take an alcohol and if we add in some nucleophile, we want that substitution reaction. All right, but unfortunately it's not going to be that easy. This reaction right here does not actually occur. And that's because in order for this reaction to occur, we would have to kick off this hydroxide here, right? We're substituting out that hydroxide. But that's not going to happen very easily because hydroxide is a bad leaving group. Okay, so in order to have a substitution reaction, we need to replace that hydroxide. That means that that would have to play the role of our leaving group, but hydroxides are bad leaving groups, all right? There's a really common feature of a molecule that would make it a bad leaving group that hydroxide shares, and that is that it is a strong base. So strong bases are always bad leaving groups. All right, so in our substitution of alcohols, we're going to have this strategy, and we're going to have a few ways to do it, but we're always going to have the same strategy, which is that first, we're going to need to convert that bad leaving group to a good leaving group. And again, we'll have a few strategies, so I'm just going to leave it as LG for good leaving group. Once we have that good leaving group, then we can treat that with our nucleophile and get our substitution reaction. All right, so the bottom line is if our goal is to substitute our alcohols, we can't just do that in one shot here. We're always going to have to first convert our alcohols into a good leaving group, and then we can do our nucleophilic substitution reactions, right? So really we're focusing on ways that we can convert alcohols into good leaving groups, and then we can just treat them with our list of nucleophiles in order to get our substitution reactions. All right, but how do we make our alcohol into a good leaving group? There's sort of two strategies that we're going to have. The first is to convert that alcohol into an alkyl halide. Alkyl halides were discussed at length in the first semester because they are good leaving groups, right? So if you have an alkyl halide, it's kind of easy to kick off that halogen and replace it with something else. So if our goal is to substitute our alcohol, if we can first turn it into an alkyl halide, then we can go from there in terms of our substitution reactions. So how do we convert alcohols into alkyl halides? We're going to have a different strategy depending on the classification of our alcohols. So we're going to lump primary and secondary alcohols together, and we'll talk about tertiary alcohols separately. All right, right? So if we have a primary alcohol and we want to create an alkyl halide, specifically an alkyl chloride, we're going to use a reagent that we're going to see a few times throughout the semester, SOCl2, what's called thionyl chloride. All right. If instead we wanted to create an alkyl bromide, we again got a fancy reagent that we're going to use, phosphorus tribromide. All right. So both of these here would be reagents that convert our hydroxyl group into a halogen, converting our alcohol into a molecule that now has a good leaving group. One of those halogens are good leaving groups. All right. So we're not going to learn the mechanism for these reactions. The thionyl chloride is actually in your textbook, but I'm not going to have that be one of the ones that we have to know here. Suffice it to say that it kind of globs onto that oxygen and converts it into a good leaving group to get kicked off. But I am going to note that these are SN2 mechanisms. All right, these were these two substitution mechanisms that we learned last semester, SN1 versus SN2. And what were the consequences of those differences? Using a primary alcohol, it's not a good example. So let's look at a secondary alcohol and perform these reactions. And specifically, we're going to look at a stereospecific secondary alcohol. All right, where my hydroxyl group, I'm giving you a particular stereoisomer of this molecule. The, what is that, clockwise, R stereoisomer here. Okay, if we were to treat this with our thionyl chloride, because it's an SN2 mechanism, a consequence of those SN2 mechanisms, what we call these backside attack mechanisms, is you're going to get an inversion in your stereochemistry, meaning that this wedged bond here is going to flip to a dashed bond or invert to a dashed bond when that chlorine's added. All right, so a consequence of these SN2 mechanisms is what we call stereochemistry inversions. All right, so then given what we've discussed, let's just complete this for our phosphorus tribromide, also an SN2 mechanism. So what would we expect our product to be? Dash to a bromine, yep. All right, so if we have a primary or a secondary alcohol and we're trying to create an alkyl halide, we're going to use thionyl chloride or phosphorus tribromide, which does these SN2 reactions to substitute out that hydroxyl group for a halogen. All right, these tend to be on the more expensive side. They're highly reactive. They have to be stored in a particular way. If we go to a tertiary alcohol, it's actually a lot easier to substitute for a tertiary alcohol. First of all, you can't really use the thionyl chloride or the phosphorus tribromide because tertiary alcohols, that tertiary carbon is not really good for SN2 reactions because it's really crowded. It's not very easily accessible. So first of all, you can't use your thionyl chloride or your phosphorus tribromide, and you wouldn't want to anyway because they're way more expensive than what you could use, which are just our simple, strong binary acids like hydrobromic, hydrochloric, or hydroiodic acid. All right, these will very efficiently substitute that hydroxyl group for a halogen. Okay, and unlike our primary or our secondary, we're actually going to go ahead and look at our reaction mechanism for these. All right, let's see if we can't reason through our mechanism here a little bit, looking at these two molecules, trying to predict what's going to happen here. So first of all, what do we know about HBr? If you're working with HBr in the lab and you spill it on yourselves, are you just going to go about your day? No, why not? It's an acid. It's a strong acid, like hydrochloric acid. Hydrobromic acid is actually even stronger than hydrochloric acid. It's one of the strongest acids that I've ever seen, like in the wild before, like actually in a lab. All right, so it is a very strong acid, meaning it's going to donate this proton. So I'm going to be breaking my hydrogen-bromine bond. All right, it's going to donate that proton. And if I look over here, what's going to be accepting that hydrogen? There's really only kind of one candidate here, which is my most electronegative atom, the only one with some lone pairs. So what's going to be playing the role of the base here is my oxygen. We're going to protonate that hydroxyl group. So that'll create that bromide ion, and everybody's going to take a second following these electron pushing arrows, give me what my organic intermediate is here in this reaction. When I'm looking at this arrow here, is that a bond breaking, bond formation, or both arrow? That would be a bond formation arrow. So I'm going to draw my new oxygen-hydrogen bond. All right, and what else do I need for my intermediate here? That positive charge. My oxygen now has those 3 bonds and only 1 lone pair. So that means it's got that positive charge associated with it. And this is going to be a strategy that we're going to see over and over again. One good way one easy way to convert a hydroxyl group into a good leaving group is to simply protonate it with a strong acid. In the next step in our mechanism, we can see why. It's actually just this one bond breaking arrow here. And what's my leaving group going to be? Water, a nice neutral molecule, not a strong base at all. A good leaving group here, a neutral water molecule. All right, so then what's my intermediate that forms? Carbocation. Somebody said it, yeah. So when this carbon gets that pair of electrons taken from it, now all of a sudden we have our carbocation. And this carbocation is the signature of our other type of substitution mechanism, what's called an SN1 substitution mechanism. Why do tertiary carbocations form, but we don't see the same thing with primary or secondary alcohols? Remember, we talked about the differences in carbocation stability. Tertiary carbocations are much more stable than primary or secondary carbocations. So we don't see any carbocation intermediates in our primary or secondary alcohols, but we will with our tertiary alcohols. They form those nice stable carbocations. And then the bromide ion, negatively charged, is going to attack that positively charged carbocation, giving us our final product here, our substitution product. All right, so for our primary and secondary, we got to use those fancy reagents, the thionyl chloride and the phosphorus tribromide. For tertiary alcohols, we can use what is practically way cheaper, just these strong acids like hydrobromic, hydrochloric, or hydroiodic acid. These mechanisms here are fairly simple for our tertiary alcohols, where the first step is to protonate that hydroxyl group, turning it into that good leaving group water. We get this carbocation intermediate that our bromide ion attacks, giving us our alkyl halide. Okay, so let's just real quick summarize our stereochemistry of these SN1 versus SN2 reactions. All right, I'm just going to kind of restate what we said up here in our notes, that these SN2 reactions lead to that stereochemistry inversion. All right, so if I'm looking about that chiral carbon, it reacts at that carbon, so I get this inversion in our stereochemistry. To be clear, by that I mean my wedged becomes a dash bond, or if instead I was starting out on a wedged bond, on a dash bond, it would become a wedged bond, right? So we're flipping the direction when our new bond forms. So then what about these SN1 reactions? All right. Previously, our alcohol that we were looking at didn't have any stereocenters, so let's pick a stereospecific alcohol to look at. It's going to be a stereospecific tertiary alcohol. All right, so what's going to happen to our stereochemistry when we treat this with our HBr? Okay, we're not going to, you could do the full mechanism totally. It's going to be this similar to what we did before, but let's just look here at our intermediate. That carbocation. Okay, so these chiral stereochemistries, our dashes and our wedges here, are a result of that tetrahedral structure of our sp3 hybridized carbons. Okay, but when we take this and we remove that hydroxyl group to form our carbocation, what do we know about the hybridization of a carbocation? These are no longer sp3 hybridized, but sp2 hybridized, meaning that when this carbocation intermediate forms, this molecule will lose any sort of stereospecificity. So it loses that stereospecificity. Because these sp2 hybridized carbons are flat. They're trigonal planar structures, which means that my bromide could attack from this side, or my bromide could attack for this side. I'm going to get a 50-50 mixture of both possibilities. Right? So what we could do, if we were trying to do things the long way, and we're going to shorten this up, but we could either show that we get a mixture of both, where my bromine is on a wedge, or a dash rather, and when my bromine is on a wedge, we get a 50-50 mixture of these two. But the shorthand for that is to simply show these as straight line bonds. All right, that implies that we have a mixture of all possible stereoisomers. So whereas our SN2 reactions, we're going to keep this phrase in mind that we got to look out for a stereochemistry inversion. For our SN1 reactions, we're going to note that they lose that stereospecificity. So if I start out with a stereospecific tertiary alcohol, I'm not going to get a stereospecific product. I'm going to get a mixture of all possible stereoisomers. All right, I will say specifically about that carbon that we're talking about reacting. If there was some other carbon in this molecule that had stereochemistry, we're not touching that one. But specifically about our carbon where we're reacting, we're going to lose our stereospecificity. Okay, so we were talking about substitution reactions of alcohols, and this was just this intermediate step that we were doing here, right? To create our good leaving group. What's up?
For SN2 reactions, if that OH bond were not stereochemic, like it was either a wedge or a bond, it was just a straight line, would we be presented with that, or is that something?
So yeah, so either it's not a stereocenter, in which case there's no stereochemistry to worry about, or if I gave you even this molecule with a straight line, that would imply you had a mixture of both, so then your product would be a mixture of both. So yes, it's only when I'm starting you out with a stereospecific alcohol that you got to worry about this inversion happening. Okay, so now let's get back to this topic of substitution. All right, we're going to take our alcohol . We're going to first treat it with, let's say, thionyl chloride. And then we're going to add in sodium cyanide. All right, so what is my product going to be after these two steps? So what's that first step going to do? It's going to take that OH group and replace it with a hydroxyl group. A chlorine. All right, so what about our second step here? All right, so let's look carefully here. Sodium cyanide, I see this in my list of reagents. And what am I going to first do to that sodium? I'm going to get rid of it. And specifically, I'm going to get rid of it and replace it with a minus sign, right? Because that's what the sodium's doing, is providing that counter ion. So the other part, my interesting bit, is going to be this negatively charged ion. And I'm going to draw out my Lewis structure here to be clear. The cyanide ion here was an example of a carbon nucleophile, so that negative charge is on that carbon atom. All right, well, what we learned about alkyl halides and these strong nucleophiles here is that they will undergo a substitution reaction. That nucleophile is going to attack and kick off that leaving group all in one step here, creating our product. All right, well, this substitution mechanism where your nucleophile attacks and your leaving group leaves all in one step, this is that SN2 mechanism. So not only was that first step an SN2 using our thionyl chloride, the one that we didn't look too closely at the details of with electron pushing arrows, for our nucleophilic attack of our alkyl halide, that's also an SN2 mechanism, right, where our nucleophile attacks and our leaving group leaves all in one step. So with that in mind, let's think about what's going to happen if I take this same list of reagents, but instead of starting out with a primary alcohol, I start us out with this stereospecific secondary alcohol. All right, same list of reagents here. I want everybody to take a second and see if you can't figure out what our product would be in this reaction. Alright, so that first step, we're going to add on that chlorine, or rather substitute on that chlorine. But importantly, because we noted that this is an SN2 reaction, I'm going to have to take that wedged bond, turn it into a dashed bond. Alright, but then when I do my second reaction, this is also an SN2 reaction. So what am I going to do to my now dashed bond? What am I going to do to this in my product? It's going to flip back. All right, so that first step flips it. That second step flips it again. And so now I have my nitrile group added onto that wedge. Whatever, that's fine. All right, and to be clear, the reason for that stereochemical inversion, again, we said that it's this cyanide ion, that's our nucleophile. Because in order to get to that carbon that it's reacting, it has to go from the opposite side of where that chlorine is, that backside attack. So that's what leads to that stereochemical inversion. So I flip it once from a wedge to a dash, and then I flip it back from a dash to a wedge. All right? All right, let's play this same game, but let's do it with our tertiary alcohol. Okay, I guess to be clear, this was primary and secondary. So now we're going to look at tertiary. to play the same game where we first convert to a good leaving group. This time we get to use just simply our strong acid HBr. And second, I'm going to pick a different nucleophile here. I want to make a point. I'm going to use a thiol. Alright, so after step 1, because this is an SN1 mechanism, what am I going to do to my dashes and wedges? So they're not going to be flipped, they're actually just going to become, it's going to ruin it, right? So instead of flipping them, they're going to become just these straight line bonds. I lose my stereospecificity. So I could have started out with my R enantiomer, but as soon as I react this with my HBr, I'm going to get that racemic mixture of both possible stereoisomers. So we just represent that without any sort of stereospecificity with our straight line bonds. All right, we're going to do this second reaction, which is also, since we have a tertiary carbon, an SN1. Okay, which doesn't really matter for stereochemistry at this point because it's all gone, but this will have another consequence here in a second. But let's think carefully. If I'm looking at my nucleophile here, specifically what's my nucleophilic site? What's going to be attacking that carbon? The sulfur. All right, my sulfur with its lone pairs is going to be my nucleophilic site, which means that in my product here, my new bond is going to be a carbon-sulfur bond. All right, but we're going to note that this is a neutral nucleophile, not a negatively charged nucleophile, but a neutral nucleophile. And when these neutral nucleophiles react, they will lose a hydrogen. So what gets, even though I start out with SH, what gets attached to my molecule here is just that sulfur. That hydrogen gets lost in this reaction. And this is going to be important to note here. Because this is an SN1 mechanism here, what's my intermediate for those SN1s? Carbocations. And carbocations are about as good of an electrophile as you could possibly have, right? So now we have a really good electrophile, which means that our nucleophile doesn't have to be all that great. So we can use not only our strong nucleophiles, but also our weak nucleophiles for these reactions as well. So for our tertiary, we can use all of our nucleophiles. All right, so water would be a weak nucleophile. We could use that in these reactions here. For our primary and secondary, though, we got to note that because these are SN2, because my nucleophile has to attack really strongly and kick off that leaving group, this will only work for those strong nucleophiles. All right, so if we're going to do a substitution reaction for our primary and secondary alcohols, we're going to use one of those fancy reagents, either thionyl chloride or phosphorus tribromide. These react in these SN2 mechanisms, which means if we have a stereospecific alcohol, it gets flipped, but then it gets flipped back again when our nucleophile reacts. If we're going to do a tertiary alcohol, we can convert that to an alkyl halide using just HBr, or hydrochloric or hydroiodic acid. Since that's an SN1 mechanism, we lose all of our stereochemistry. And because then that substitution is SN1, we can use all of our nucleophiles, including our weak ones, in order to do our substitution. All right, so first strategy for substituting alcohols is to first convert them into these alkyl halides. All right, we're going to have another strategy to convert our alcohols into good leaving groups. Using what's called tosyl chloride. Okay, so this is a very special reagent here. Its goal in life is to convert a hydroxyl group into a good leaving group. All right, so let's just take, let's note that this strategy would work for primary, secondary, or tertiary alcohols. Right, so if we treat our alcohol with, again, what's called tosyl chloride. Tosyl chloride is a big, ugly reagent here. We got a benzene ring. With a methyl group on one side. And then this sulfur, kind of like a sulfonic acid group, but instead there's a chlorine on there. All right, what happens is that this tosyl chloride group, actually just the tosyl group, is going to attach itself onto our oxygen in our alcohol. So now that oxygen is bonded to that sulfur. Still got all this other crap going on. Okay, and the whole point here is we created this big ugly monster, but this thing right here is just about the best leaving group that you could possibly have, right? So by treating that alcohol with tosyl chloride, we have created this fantastic leaving group. So then we could turn around and treat this molecule with our nucleophile, and we would get our substitution reaction. Now this is a little bit of a ridiculous big ugly molecule to be drawing, so we have a shorthand for this. All right, I could draw this exact same thing, but instead of using Lewis structures, we represent that tosyl chloride molecule with just TsCl. So then if I want to draw my fantastic leaving group, I would draw my oxygen, and then just note it's got that Ts. So Ts stands for that sulfur and benzene ring part of my molecule. So these are equivalent ways, one using Lewis structures, one using our shorthand here. So then what about our stereochemistry? Meaning, what if I started out with one of those stereospecific alcohols? And I react that with our tosyl chloride. Okay, well, importantly, this molecule is not reacting at that carbon, right? My carbon here isn't what was reacting in this reaction here. It was my oxygen of my alcohol group. So since there's no reaction occurring at that chiral carbon, we don't have any sort of a stereochemical inversion. We just get that same product, or rather that same stereochemistry in our product. So our stereochemistry here, we get no inversion. It's not even reacting at that carbon. Okay, so then let's compare our substitution methods. All right, we're going to take this same stereospecific alcohol, and in the first, we're going to treat it with, let's do our phosphorus tribromide. All right. Then we'll do our hydrogens. I guess I would do NaSH. And then let's do the same thing, starting out with our same alcohol here, but instead of converting it to an alkyl halide to make it a good leaving group, let's use that tosyl chloride. All right, so both of these cases, sodium, hydrogen sulfide here, I'm just going to replace that negative charge. If I do this top root here, after that first reaction, what am I going to do to my dash bonds? I'm going to flip it to a wedge. And then after I add my nucleophile, what's going to happen to that wedge bond? It's going to be flipped back to a dash bond. All right, so since both of these steps were these SN2, we see an inversion and then an inversion back. All right, so the big difference here is if instead I use that tosyl chloride method, what are we going to do to our wedge? No, it's not a wedge. What are we going to do to our dash? It's going to stay the same. I'm just going to glob that TS onto that oxygen. All right, but then when I do my second step, I still have that SN2 mechanism. So now I'll see this stereochemical inversion from a dash to a wedge. Because there was a negative, it wasn't a neutral nucleophile, it was a negative nucleophile. So if instead I was using SH2, the neutral version, that hydrogen would have to leave, but it was already had a negative charge, so I don't have to take a hydrogen away. All right, so just know when we're comparing these substitution methods, we would get a different product, same thing added on to our molecule, but different stereochemistry depending on which path we chose. Cool. All right, we'll pick up with this next class and finish up our alcohols chapter. What's up?
So if it was SH2, only one hydrogen would leave, so you get the same product, right?
Yep, exactly.
Hey, how can you change your oxide?
Because it just fits in. So I go to City after this, and it just fit into my schedule way better. It was hard to make it over there on time.
Yeah, I see. All right, dog. We can do it.
Yeah, have a good one.
See you on Friday after.
All right, have a good one.